Hello, everybody. Good morning. Welcome to this second webinar organized by Animal. Animal, like you should probably know already, it's a European project funded by the European Innovation Council, which is looking into seawater electrolysis, or like we like to say, like making clean hydrogen from dirty waters. In this second series of the webinar, we have one of our researchers, Suhas Nuggehalli, who's working in EPFL in Switzerland. EPFL is one of our 11 partners in Europe researching together to put together an electrolyzer that can work with seawater. And Suhas has recently published a paper, and he will tell us all about it today. The paper is about the simulation of membrane electrode assemblies, which is basically the sort of sandwiches that we put together with two electrodes and a membrane to make the electrolytic reaction happen and make green hydrogen, which is a challenge, especially when you're trying to make this reaction with seawater because of all the complications of having impure source of water to make the green hydrogen. So, Suhas, welcome to the Animal webinar, and thank you for joining us. How's
Thank
everything?
you. Yes, everything's going great. Thank you, Fernando. It was quite nice to organize this, and I'm happy to present whatever we have and share it to the public.
Yeah, we're
With
very
knowledge.
very happy to have you here. It's only our second webinar, so we're sort of experimenting with the format. Well, we're very much looking forward to your presentation today. So, without further ado, I think the floor is yours. Really looking forward to hearing more about the paper and the details of the simulations.
Thank you very much. I think I'll start with introducing myself a bit. I'm Suhas. I'm a PhD student with Professor Jan van Herle at EPFL. We are part of NML working on seawater electrolysis. And as a part of this project, we ran a simulation using uh, various tools, different tools, to identify and map the membrane electrode assembly performance of an electrolyzer. So, what exactly is the basic working principle of an electrolyzer? Is that first thing we need to know that it's a device that is predominantly used to split water and produce green hydrogen. And these electrolyzers, they have multiple functional layers, as they call it, which performs different functions. Usually, it consists of a polymeric or a plastic membrane sandwiched with some metallic foams, sponges, on which we have electrocatalysts deposited. And these electrocatalysts, they help in splitting the water to hydrogen and oxygen. So then you can imagine that it's a sandwich of metal foam, polymeric membrane, and then metal foam. These historically come in different configuration. The one of the oldest configuration or the electrolyzer devices are the classical alkaline electrolyzers, which use aqueous potassium hydroxide, high concentration salts, with a small gap between the a separator, which basically separates the gases that are evolving in the two chambers. So we send in water here in these two chambers, and then you apply electricity, uh, preferably from renewable sources. And then you have the electrocatalyst, which are at this junction here, performing the water splitting reaction, producing hydrogen and oxygen. Similarly, this old, I think it's more than 100-year-old technology was advanced further to eliminate this gap for various reasons. And then you have this zero gap configuration. Again, the electrocatalyst layer now being slightly closer to the membrane, and then you have similar reactions happening. So, but these separators, they have drawbacks because they have pores in them, and then there are chances that the hydrogen can cross over to the oxygen side, meaning that the this results in a safety issue, because concentrated hydrogen and oxygen is an explosive mixture. To eliminate that, a different technology which conducts protons was invented in the 1980s or 1960s, if I'm not wrong, which uh, which is called as proton exchange membrane electrolyzers, using platinum group metal catalysts. And these produce dry hydrogen on one side, while allowing for pure water feed on the oxygen side. So this also functions as an electrolyzer, quite a good one. But the biggest drawback is that these polymers have PFAS, basically fluorine-rich polymers. Also, they use platinum group metal catalyst. S- While you do not need platinum group metal catalyst in this alkaline electrolyzer format. So recently, research has developed new technology that combines the advantage of the two systems having a polymeric membrane with in an alkaline system using non-PGM electrocatalyst, which can reduce the overall cost of the system as well as uh, uh, toxicity, because these membranes need not have fluorine. They need not have fluorine in them. So meaning that the exhaust or whatever the things that are the waste that comes out of this device is generally clean. And then you have basically the chemistries where you have the hydrogen evolution happening at the hydrogen electrode here, and then the oxygen evolution happening at the oxygen electrode with some stoichiometries. But all of them, irrespective of what technology it is, they effectively split water to hydrogen and oxygen. And then why is the need for simulation? Why is there a need? Because basically, as you see that these layers have complex, there is a interconnection between the bubbles evolved due to water splitting, because hydrogen and oxygen evolve as bubbles. And then you also have some sort of chemistries happening in these layers which help in uh, splitting of the water, which need not which are complex to explain. So the simulations can couple the fluid dynamics which are associated with the bubbles, and then also the electrochemistries which are largely defined by theories, and then identify performances which can help reduce experimental cost, because assembling and creating new layers are pretty tricky and expensive. So in our methodology, basically we developed a small model, 1 cross 1 centimeter, and then we ran it with coupling with the computational fluid dynamics and electrochemistries, and then we evaluated this with the experiments. And then if the model had a close tolerance with the results, we moved further on to the sensitivity analysis, and then we arrived at a ranking table trying to map all these performances or performance affecting parameters. Here is a representation of our modeling domain. We had 1 cross 1 centimeter cell area with 370 microns of thickness, KOH flow rate from bottom to top, and then the anodic and the cathodic chambers with the assumption of membrane thickness of 60 microns, which is pretty much the average membrane thickness in AEM electrolysis. Here are the first results that we procured. The blue curve shows the experimental data, and the red one is the model representing the experimental data. You had the fairly good, reasonable overlap. The materials chosen to validate experimentally were ranitol or nickel felt, a membrane from dioxide materials X3750RT, and nickel iron oxide on stainless steel. And here what you see is the evolution of gas fractions in the cathodic and the anodic chamber, which pretty much follows the stoichiometry. As you can see that the hydrogen side has a larger gas fraction compared to the oxygen side. Well, the continuous phase, which is phi c here, is the liquid phase, and the dispersed phase is the gaseous phase. They sum up to 1, and this is how the gas fractions were calculated and evaluated from bottom to top. And you can see that the gases tend to go towards the exit of the MEA simulation. Current density also has an effect. So when we apply a certain, we have to apply external power to split the water. So this translates directly to current density, which results in voltage characteristics of the cell. So we have control on the applied current density. So when we apply a certain current density, it also has an effect on gas fractions. And this is a cool study because the current density is controlled by the electrochemistries as well as the evolving gases CFD that is involved. So once we had a fairly good understanding of the simulation, we moved on to perform a sensitivity analysis by changing the state parameters. For instance, we changed the temperature from 20 to 60 degrees in 1 molar KOH at 1 ampere per centimeter square, and we could see that at higher temperatures you have better evacuation of the bubbles from the catalyst layer. So the catalyst layer is close to the membrane, meaning that this is one of the reasons why we have enhanced performance, because the mass transfer kinetics are improved. And now we can visually see this. As an effect of pH as well, we fixed a certain voltage, which was 2.5 volt, to see how would the pH, or basically the amount of potassium hydroxide salt in the water, affects the performance. So it basically shows that the more potassium hydroxide you have in the salt, the more is the hydrogen gases evolving, because this directly translates to increasing current density. It was not really much of a surprise, but it was a good thing to map and identify for these material combinations what could be the potential range of operation of the electrolyzer. So pH 12 is really pretty much no hydrogen evolution or really low, and perhaps pH 13 could come into this classic alkaline domain. But then I think anyway, any simulation further, any concentration less than pH 14, it's quite tricky to achieve with these standard commercial materials. So based on all this data, we also manually or in the simulation change the membrane thickness by changing physically the thickness of the membrane, and then we saw that thinner membranes have better performance, thicker membranes has worse performance. And this was nice to know, because I think overall the effect of membrane is also predominant compared to the pH. So this study was done in 1 molar KOH. There is also a reason for electrolyzers to be operated with only one side fed, uh, similar to the PEM electrolyzers that I showed in during the introduction, that we do not send liquid electrolyte on both the sides, because the evolving hydrogen would be drier if you send the liquid only on the anodic side. So this study was also performed, and we found out that the effect of dry cathode versus wet cathode is slightly low compared to the other parameters that we saw till now in the sensitivity analysis, predominantly because the membrane has a very good water uptake that humidifies the hydrogen side where the water molecule is necessary to split and evolve hydrogen. Further, we changed the flow rate between 1 to 2 ml per minute in the wet cathode configuration. We also saw quite minimal effect in performance. So larger flow rates do have an improvement in performance, but if you are not in the mass transfer region, this barely has any effect, provided the membrane has sufficient enough uh, of water available to split. So based on the ASR, which is called the area specific resistance, basically the slope of the IV curve here, what you see is that the potential versus current density, if you fix a point, we fixed 1 ampere per centimeter square for the parameters where we could fix current density, and 2.5 volts for the parameters where we could fix the voltage, for instance. Uh, yeah, for instance, KOH concentration, we did not reach 1 ampere per centimeter square, but we see that based on the model, uh, the between 12 to 14 PS, 12 to 14, KOH has the highest effect, followed by the membrane thickness, temperature, dry cathode feed, and then the KOH flow rate. So this kind of gives us an operating profile to worry about, to research on, to know that the model predicts quite well what could be the effect of these concentrations. And for future work, once we have now that we have validated this model, what could be very interesting is to apply DOE techniques to identify operating maps of such a material system to see whether certain targets can be met, which will further enhance in developing, uh, uh, let's say, smarter control systems for the electrolyzer as a whole when you have a stacking system, and also to adapt the MEA model for the seawater electrolysis, which is practically the scope of NML. As And I think the 1 molar KOH and basically the KOH related studies was very relevant in identifying different parameters that affect the MEA performance in the model. And this work has been published in the Journal of Power Sources. And if anyone is interested, please go ahead and take a look at it. It's much more detailed. The model structures are much more explained, and and you can get more information there. And feel free to write to me if you have any questions on this. Thank you.
Thank you so much, Suha. So if anybody wants to read the paper, there's a link in the chat of the YouTube video that goes directly there. And then we also wrote a blog post on our NML website. So that's nml.eu, which is also linked in the chat. So now we've got time for questions for Suhas. If you have any questions, please feel free to drop them in the live chat on YouTube, and then we'll take a read and pass them on. But before we go to the audience questions, I've got like a sort of like a big picture question going more to the how these simulations fit the wider idea in animal, which is working between many groups in Europe to put together a seawater electrolyzer that actually works. So haven't seen a lot of seawater and chloride ions along the simulation. So I'm assuming that's the next steps. And then also, how do you sort of feed from the results of the other
Mhm.
partners to make sure that they match the simulations of the model that you're putting together in EPFL?
Mhm. That's a very valid question, Fair. I think it's very interesting time to have had this simulation, particularly for a couple of reasons, because there are so many electrocatalysts that are being developed right now, and with the various from the various partners of NML, and also a couple of membrane configurations. And what we could do is that usually when people validate the performance of the electrocatalyst, it's either in a 3 electrode setup, which is a simpler version compared to a membrane electrode assembly study. And then we can take this data directly from that test, preliminary test, plug it in our model, and expect an MEA performance, for instance, because when you develop the model, we develop it component wise. So we develop one layer, anode, cathode, and then the membrane separately, and then
Mhm.
bring it together. And this is very interesting because this means that if and then these electrocatalysts, they also have a interaction with the membrane, and this interaction can be captured in the MEA because we also have uh, s- uh, a, l- a chemistry that is involved that deals with this interactive layer between the membrane and the electrocatalyst. So it's
Hmm.
generally that describes the ionomer configuration in this case. So for instance, in the commercial materials that we procured, we saw that okay, practically no performance in pH 12. But
Hmm.
if we get new very well developed catalysts from the other partners, and I think if they show really promising results in the three electrode setups, then I think that is a great start, because then we could predict performance instantly by changing
Hmm.
certain electrochemical parameters in our model.
Hmm.
And
Yeah, I was gonna say, like, I mean, actually that ties in very well with my next question, which is about changing the parameters. Because I mean, when from like an external point of view, when you see the model and you see the electrolyzer, like it seems gonna be complicated to change a whole material in the model. But I'm assuming that's just changing a couple of certain descriptors in the model, and then
mhm,
like electrical charge or like how conductivity, things like that. So how does it work when you
mhm,
want to change the materials that you're using? So, say instead
mhm,
of using the nickel foam that you use
mhm,
in the standard simulation, you want to use some of the electrodes that we're preparing in animal. How easy it is to change and
mhm.
adapt the model for that?
So that's a good question, because the intricacy is that the first data that we could potentially get from these three electrode setups is the exchange current density. So if you put exchange current density value in the model, we can predict the next performance that comes. And this is, I think, done simply through a TRAFL scan that we can do at very slow scan rates, couple of scans, then we with ohmic corrections, as they say, and then we could have, let's say, electrode performances coupled together MEA performance. Afterwards, now, when you have different electrodes, meaning that we are working on these porosities of these layers here that you see as well in the PTL layers, as they call it, we can scan this using a tomographic facilities that we have here that gives us a difference in the conductivity between the bulk, for assuming that, let's say that you have stainless steel, which is a solid rock, and what is the conductivity of this solid rock, a cube, and compared to all these porous materials that we have, because the sponge is basically material removal from this block of stainless steel, and then this affects the electrical conductivity, and this we can also input in the model as well. And so basically minor tiny parameters that we can analyze using SEM or X-ray tomography, and then it allows us to scale up really fast, because once you have the porosity, the current density, the conductivities, and also diffusivity, with these parameters, if we plug it in the model, it will say how
Hmm.
effectively the bubbles are evacuated in these electrodes, and
Hmm.
therefore we complete the coupling loop between the electrochemistry and the CFD.
So it's just about finding the right parameters and then detecting them in the actual
Yes,
electrodes and membranes, and then just
exactly.
bringing those back to the simulation so we can redo the whole
Exactly.
thing.
Exactly. It's about measuring the right parameters, I would say,
Hmm.
and in the right way, because I think there are a lot of methodologies on how to measure these materials, and I think there is one from Journal of Power Sources as well, that they
Hmm.
give good practices for fuel cells and electrolyzer systems, and we followed that in our article to measure these exchange current densities, for instance, while plugging it in. And so if so basically a protocol that is recommended by Journal of Power Sources, and
Hmm.
then we adapted that. So I think if I think the consortium will really benefit through this, because uh,
Hmm.
there has to be catalyst screening, which is, I think, now the tricky part, that because the catalyst has to work in seawater. And
Hmm.
the next thing that you referred is also chloride ion. So these ions directly relate to corrosion of the material, so changing conductivities. So this is also something that we would have to study and explore. It's
Hmm.
new, and we'd have to see how to incorporate in the model. Usually, we can add certain external equations that we
Hmm.
develop on our own. Uh,
Hmm.
Perhaps if we develop a corrosion rate or a corrosion prevention rate in our studies, because we would have protective coatings on these materials, then we could plug this in the model as a correction factor. But this correction factor is not an arbitrary correction factor. It follows the chemistries of corrosion that we test
Hmm.
separately. And then,
So yeah, so sorry, I didn't want I didn't want to interrupt. We're just
yeah,
getting questions from the audience, which I think
okay,
is great because it's
yeah,
that's what makes this webinars a bit more interactive. So we've got someone asking about polarization curves, which
hmm,
I'm assuming is referring to one of the previous slides.
okay,
And the question is why in OCV and low current the voltage is less than 1.4 volts.
hmm,
So I think maybe if we show those graphics again, we can explain
yes.
why
For
that's
instance,
happening.
this one, yeah. No, I think we just assume the OCV to be 1.23. I think it depends on how you define the OCV, whether you base it on HHV or LHV. And I think there are competing theories for this. I'm not really quite uh, sure about what it is, but experimentally, when we perform a scan, we always perform from 1.1 volt to see how the evolution happens or which regimes we have evolution. So
Mhm,
it's but in the model we start from 1.2. I think this was because of the definition of OCV based on LHV, if I'm not wrong.
mhm. Cool. I hope that answers the question as well. If there's any follow-ups, feel free to drop them in the chat. We've got another question from what looks like a company, which is great because one of the goals of ANML, of course, is to promote technology transfer and promote partnerships with companies throughout Europe. And this is a question about one of the descriptors we were talking about, in particular pressure. Like how do you simulate the pressure within the MEA and within the electrolyzer? Because if you're generating gas bubbles, audience is wondering about the the effect of bubble size on pressure and how that affects
Mm-hmm.
electrolysis.
So I think in general there is always a penalty because okay, when you look at the system level, you feel that pressurizing is the better option because you would reduce compressors required afterwards or the energy input to the compressors. But for the membrane electrode assembly, when you pressurize, you have a drop in performance. And this comes as a thermodynamic penalty because of partial pressures or whatever, however you would like to call it, change in concentrations. But how this we physically compensate is that usually the pumps, we assume in the modeling domain, the pumps are able to overcome the pressure. So you would have a net outflow irrespective of how much pressure you have in the system, that you would have resulting a pressure gradient, let's say of a few millibars, that allows the flow to go through. But we were not able to test it in our experimental cell, and this is why we have not yet extended the model to the pressurized system, because the electrochemistry is already
Mhm,
was very challenging enough. But it is just another parameter that we input, and then I think at the MEA level you would see a drop in performance because of a thermodynamic penalty. But
mhm,
overall in the system, I think after 5 or 10 bars, it makes I think up to 10 bars it makes sense to pressurize an AEM system, because afterwards the cost of compressor energetic cost of compressors are lower. The compression issue
mhm,
always comes while compressing from atmosphere to 350 bars or 700 or whatever the output pressure that is required.
mhm. We keep getting questions from the audience, which is great. I'll go back to this pressure thing because I've got a question that is sort of related to that. But we got a question from Karam Yassin, who's asking if you could describe again the computational domain for
Hmm.
the membrane electrode assembly. Um,
Yeah,
they're also thanking you for the talk, so that's
thank
good
you.
feedback there. So basically, they're wondering whether it's a 3 layer or 5 layers MEA,
Hmm. Hmm.
and then, in particular, how are you solving the transport equations? Just
Hmm.
a kind of reminder before you answer that if you want to read the full paper, thanks to ANML and the funding from the European Innovation Council, the paper is in open access, so you can go to the link that we've posted on the chat, or you can go to our website and find all of the papers published in the project in open access, so they're free to read and consult by everybody anywhere in the world. So if you want to go back to that, that's an option too. But then again, Suhas,
Hmm.
we can go back to the model and explain how many layers it
Right.
has and why
So
that matters.
yes, yeah. So I think in principle it has 5 layers because we assumed infinitesimally small catalyst layer in the first place to have some sort of an ideal catalyst performance, and but this 370 microns that we see is basically the GDE thickness. So we assumed a layer right close to the membrane. So this acts only as a support. So basically a CCM configuration you could assume. And then the domain was 1 cross 1 centimeter. And the coupling happened, we did the Euler model for the CFD. And then the fuel cell and electrolyzer module from COMSOL that we coupled it. And I think this one includes electrochemistry for the MEA simulation here. So we tried both 5 layer and 3 layer, and 1 centimeter square was chosen to mainly prevent mass effects in our system, in our experimental setup, because the requirement is to validate the model at a really small scale first so that we have the coupling right, and then we are not let's say overfitting any errors that might cause because of the size of the system, because once we go for a larger size MEA to validate experimentally, you have unknown mass transfer concentration gradient effects, and we wanted to eliminate that, and that's why 1 cross 1 centimeter square. And the next step, if you go for a larger area, then we would know that the rest of the issues is coming from concentration and mass transfer. And hopefully this
Mhm.
answers the question.
Yeah, I mean, we've got a follow-up question about the pressure and the thermodynamic penalty, but
Hmm.
I don't know if we want to address those or sort of go to the ones I had about the size of the simulations because they kind of fit what we were just talking about. But maybe we can answer the question first. When you were talking about thermodynamic penalty before, uh, were you referring to the energy that's needed for compression of the gases? Like what were you referring to exactly? That's a question that we got from our audience today.
I see. No, I think it's both, because you have also slightly a performance loss in the MEA. It's still not clear why this loss comes from, but then it's also, I think, in the system level, it I mean, if it makes sense to have a little bit of I think so. You have a thermodynamic loss happening in the MEA through the electrochemistries. So basically, perhaps Gibbs related losses. I am not an expert on this. I have to verify this. But then I think then you have a system level losses as well, which I think is completely different. But I think intrinsically there is MEA performance loss because of compression, and this is
Mhm.
something that we I would have to develop my knowledge further on. Yeah.
Okay. So if you're interested in getting in touch, this is like to the
Yes.
audience basically and the people asking the questions. It's fine to drop us an email to our like consortium. The webpage has a contact form. And then otherwise we can put you in touch directly with the speaker or like any of our researchers. So if you want to chat a little bit further or maybe establish a collaboration, we'd be happy to do that. Since we've got the slide on the screen now about the actual electrolyzer, I think maybe that sort of brings up a question that I had about the difficulty of the simulations. Because the simulation we're
Yeah.
doing now is like 1 square centimeter,
Right.
which is sounds tiny, but it's already a lot to know what's going on in that system. But I was curious
Right.
of like how much actual computing time
Mm.
and resources it takes to
That's a good
simulate
question.
something like this.
That's a
And then
good
also like
question.
how
Yeah.
do you escalate it if you want like
Hmm.
a bigger
Yeah.
electrolyzer, is it okay to simulate like a lot of tiny ones, or do we need to make a model that is bigger and therefore
Hmm.
maybe require like HPC, high performance computing,
Yeah.
and bigger resources to actually
Hmm.
simulate the
Hmm.
bigger electrodes and
Right.
electrolyzers?
I think it's the answer is straightforward here. The more CPU and more RAM you have, the better. It's always better. And COMSOL right now does not do hyper threading, meaning that when you have a CPU, it comes with number of cores. Let's say that you have a 12 core CPU, and then there is hyperthreading and it becomes 24 cores, meaning that each core is operated as two independent cores. So this is not yet available on console, so meaning that you are limited to physical number of cores. And Euler is just way too intense for for this, because here I think we had I think 1 million or 2 million nodes, which was already computationally intense, and we performed the calculation on a 16 GB RAM with the 8 core
Hmm.
processor. So I think our best simulations took 5 days to converge.
Hmm.
So it was lack of computation resources that also made us to stay in this domain. But
Hmm.
now I think we have improved on that, and I think for a larger area, you should probably reduce the mesh density, and I think it's absolutely fair to reduce the mesh density and also move away from Euler module model or
Hmm.
Euler physics to mixture based model, because I think
Hmm.
that's a bit more uh, easier to converge and a good approximation to the exact chemistries and exact flows. And you
Hmm.
always have this larger correction factor, but then if you're able to associate it with something, then I think
Hmm.
these correction factors get a definition as to what is this related to.
Mhm. No, but that's really interesting because I mean, you basically did the simulation in what sounds like a household computer because like
Yes.
16 gigs of RAM and 8 cores, like that's almost every
It was tough.
computer
It took us
nowadays.
1.5 years to finish it. So it
Mhm.
was
Yeah,
tough.
yeah. Yeah, but I mean that also brings me to my next and maybe final question because it's we talked a lot in the preparations of this webinar about scale up. So I've got the question. So like, okay, first, how do we scale up the model in a
Mhm.
sense that, um, like you said, maybe reducing the mesh, maybe trying to find time or grants to apply for like high performance computers so we
Yes.
can get
Yeah.
bigger simulations running.
Hmm.
And then also, how do we scale up the
Hmm.
electrolyzer? How can the models that we're doing in a computer,
Hmm.
how can they help us scale up the fabrication of electrolyzers from, the
Interesting.
tiny lab size that we're testing to
Hmm.
the bigger size? How can we get any hints on like, maybe this material is working now in the lab,
Yeah.
but may not work in a bigger scale
Hmm.
because the computer says so? That's yeah.
Yeah. I think I would be cautious in predicting performances. So what I would like to stress again is that it's a performance map. So it's a good tool for selecting the materials, let's say. And then once you have material selection, then it's reasonably risky, of course, to assume that these materials will perform at high scale or larger scale. But the moment you go to scale, it's less of chemistries and more of deposition techniques that come into picture. So if your cell MEA, let's say that the model predicts 1 cross 1 centimeter, great performance, and then you are able to reproduce this in a 1 centimeter square cell as well. I think that is a really good cell to start with. But then the coating techniques to fabricate large scale MEAs, the inks are different, the spraying and the coating methods are different, the point of contact between the GDEs, the stack fluid distribution, how the things that come into your MEA is different. So right, so these also have an effect, because in the model we assume uniform distribution, uh, good dispersion of the bubbles, and these assumptions we are able to do it because it's 1 centimeter square. So if in the electrolyzer stack development you can ensure that the stack can give all these parameters into the MEA, it is extrapolatable for large area easily. But then you always have a few millivolts, few microvolts of losses that cascades on a stack level. So I think it can be a great tool for selection, and it has to only come through experiments for validation of the model, that okay, the model
Mhm.
predicts well. And then once you have, let's say, the first trial of large area, let's say one cell, large area, whatever the area, and you validate the model, and then I think you can try to play at that scale as well.
Mhm. No, that's really interesting. 'Cause like you were saying, sometimes when we come to larger scales, there's gonna be a lot of things that may not be taken into account by the initial model, like how you manufacture the electrodes, how you manufacture the membranes, and those are things we're looking into in NML. We're looking into new ways of manufacturing the electrodes, and especially new ways of manufacturing the membranes with techniques such as electrospinning and a couple of the techniques to make the membranes, sort of, because we are not using the fluorine, we sort of need new techniques to overcome that. So yeah, that's really interesting. I think with that note, we can probably close the session for today. I think it was a very interesting discussion, and I love learning more about the paper. It's a really cool study, and I'm sure that there's gonna be many more coming up, especially the moment we start using, seawater in the studies, and seeing what happens to those chlorine and chloride ions, and see where they go, and if they affect corrosion, or if there's like a parallel reaction for, chlorine evolution. So
Right.
that's going to be very interesting. I think if anybody wants to stay in touch, I've mentioned the webpage already a couple of times, so you just should go to nml.eu. And you can also subscribe to our newsletter and our webinar newsletter, which will let you know when the next webinars will take place. We are planning one in a couple of months, so ideally before we start the summer. And yeah, stay tuned for that. And if you have any suggestions for topics, or ideas, or people that you want to see in the webinars, we're also, very transparent and open for suggestions. Just drop us a line, and we'll consider that. There was a lot of discussions with industry during the chat and the questions. If you want to collaborate, please drop us a line. We'll put you in touch with our innovation and technology transfer managers to see if we can find a way to collaborate. And last but not least, of course, thank you so much, Suhas, for joining us today, for preparing the
Pleasure.
presentation, and for you know delving into so much detail of your model and why it's going to matter for the scale up of seawater electrolysis. Thank you so much, Suhas, for
Thank
joining
you
us
very
today.
much. It was a pleasure to be here. Thank you, Fernando. Yes.
Thank you all for joining. Subscribe to the newsletter, and see you in the next webinar.
Thank you.